All right. Hello, everyone. I'm glad to see all of you here this evening. I want to welcome all of you who are watching remotely. This is a very important lecture tonight, and it's going to be given by Chao, whom I will introduce in just a minute. I want to thank our sponsors, Gazette Newspapers, and the Marriott Courtyard downtown. Come on in. Chao is quite a remarkable guy. He's the founder and the CEO of Seatrec, which is a spin-off technology startup from California Institute of Technology, and it has a goal of providing clean, unlimited energy to power underwater drones for ocean exploration. The single limiting factor, biggest limiting factor of ocean exploration is battery life. As you know, this aquarium has been involved in ocean exploration since 2013. We held the first national forum on ocean exploration ever in the United States, and we participated in all of ones since then. And Chao has his PhD from Princeton, and he was at NASA Jet Propulsion Laboratory for over 20 years, did a number of important projects there related to the ocean sciences. And he left there to start this new company, which removes the limit of battery life, and it essentially provides unlimited energy. And just think of what that can do for ocean exploration. It's a great, great story. It's a story that we want to tell somehow here at the aquarium because we think it is so important. And we're going to be working with him on telling that story. It has great implications for ocean exploration, for monitoring offshore aquaculture operations, virtually anything where you're going to use drones or other submersible devices to figure out what's happening in the ocean. So please join me in welcoming Chao to the aquarium.
Thank you, Jerry, for the kind introduction. Thank you for coming. Let's see. Oops. It's my pleasure to be back as a father of two boys, and I used to come here and during the daytime. So it's first time to come in for the evening. It's remarkable to see the facility and how it's changing over the last decade or so. Both my boys are graduated from college, so I didn't come here for the last many years, so it's great to see the new exhibit and changes. As I see my two boys growing, I've been reading all the books about Curious George, right? So humans are, in general, very curious. We are driven to explore the unknowns and to discover new worlds, right? So that's kind of driving my curiosity to be an oceanographer and then to study the Earth from space. This year, as we celebrate our 50-year anniversary land human on the moon, there's a new race into space. Both U.S. Space Agency, NASA, and many other countries try to go back to the moon, and then eventually we send people to Mars. And as I counting recently, there are almost more than 50 companies, startup companies in the last decades, and try to develop the technology required to deliver cargoes, send robots to the moon, and then eventually to Mars. And ranging from a number of different launching vehicles to big data, and not only understanding and then try to send people to the moon and then to space travel to Mars someday. And I heard the ticket is for sale already. So you can reserve your ticket and then ticket going down every decade. I'm lucky to work with many of the rocket scientists and my peers, 5,000 employees in Jet Propulsion Lab, a lot of colleagues being a rocket scientist to develop the robots sent to the Mars. And I have the opportunity to work with them to study Earth from space. There's a number of different satellites. This is just a summary list of the different satellites we launched over the years. Study atmosphere on Earth, solid Earth, monitor earthquake, monitor clouds, measure the rain, and then study the ocean from temperature, sea level, productivity, ocean winds. And then most recently, before I left JPL, I spent 10 years to launch a satellite to measure salinity from space. So you can monitor the salt concentration at the sea surface from hundreds of miles in space. That's another conversation, so afterwards I'll be happy to chat with you how to measure salinity from space. So it turned out there's such a technology breakthroughs, and then as a curiosity-driven scientist, on land there's not much left to see, right? So if I go to open my computer, I can watch the Aquarium of the Pacific, almost every angle I can rotate, except I can see every corner. If you go out for lunch, coffee, and if the satellite fly by, where see you? So there's very little secret left on land. So where next to explore, right? So ocean is obviously the next frontier. It's the last frontier on Earth. And you probably heard the saying, we know more about surface of the moon, surface of Mars than the Earth. So both the moon and the Mars surface is 100% mapped. So we send a lot of satellites to map the surface. I'll just give you the magnitudes of the moon. We map to the resolution of 10 meters. So that's how we can land the vehicle on the moon. And then on Mars, it's 20 meters. So I give you a relative number on Earth, on the seafloor. We only map 5% of the ocean up to today. And then to give you a spatial scale, that's translate on average 5,000 meter resolution. So if I take the right-hand panel showing an area in the Southern Ocean between New Zealand, Australia, if I drop in the map of the USA, there will be big part of the ocean like Wyoming, never been mapped before. So imagine that's 1 pixel in the seafloor we know. So just to give you an idea how poorly we know as ocean. Not only the seafloor we don't know, there's a lot of property of the water we don't know either. The most recent cases of the Hurricane Dorian and the intensification over a short period of time is poorly predicted, partly because we know very little about how deep the warm water will penetrate. So we can see we can measure the temperature from space, surface temperature, but we don't really know how deep that warm water will be. That's provide the feel of the intensification of the hurricanes. And then you can imagine over 1 million people being evacuated, and then you can imagine every kilometer you improve your forecast on how much you translate into savings. The entire damage is over $7.5 billion. That's more than the annual budget of the National Ocean Atmospheric Administration. 50% of the NASA's budget of the damage of one single hurricane. Another example you can think about, if I drop something in the water, the chance is you will not find it, right? So just because we have very limited access, it's just difficult. So you can see this is particular operation. US sent 1 big ships, 1 big robots, try to look for this black box over 30 days. And then you can imagine all those little blue areas, they can search little foot stamp size area per day and then try to map in the entire Indian Ocean. It's almost impossible to search unless you know where it is located. So just to give you an idea how much we know about our own ocean on Earth. So with that as a background, the UN have decided the next decade will be the decade of the ocean. So if you're not aware, starting 2021 for the next decade. And we want to work with the international community to focus on sustainable development, to have a clean ocean, right? And we want to have a healthy, resilient ocean. We want to have a predicted ocean so we can make better decisions. And we want to be a safe ocean to support navigation, transportation. We want a sustainable and a productive ocean so we can have enough proteins and food in the future to support ocean farming and provide the food for the increasing population. And we want to make the ocean transparent. Think about it. Ocean is opaque most of the time. We cannot see through the seafloor. And and most of the time it's not accessible. So those are the guiding principles over the next decades the international community will work towards. Ocean is difficult to access. We know that 150 years ago since the first expedition. This is a famous Challenger expedition in 150 years ago, using a number of ships sailing around the globe to collect data, to map the seafloor, to find out new species. And you can see it's a very long operation over almost 2-year period. And because of the technology back then, a lot of people cannot return. It's a hard job to go away from land to collect this information, follow the trajectories, and then go around the globe. And turned out 150 years later, we use similar technology to access ocean, except the ship is modern, it's safe, relatively safe. And this is an international program, try to map the ocean for the first time. And I have dozens of big ships involved. You can see the huge vessel take 20, 30 scientists at a given time. And you can almost write a poem when a calm day, you see the beautiful scenery and scientists working in the deck and collecting data. And then most of the time is right-hand side, and it's hard work, right? So big wind, big waves. And ship is expensive to operate. So typically costs, let's pick a round number, $100,000 a day for a big ship for 20 people to work on board. You can lower this instrument down to the seafloor maybe 4 times a day. That's translate for every data point you're collecting is a huge amount of resources being costed at sea. So if you believe someday you're going to receive the delivery from Google and then your FedEx arrive in your back door, a robotic revolution is coming to our door. It's coming. Gonna have drones take pictures in your backyard, and it's going to revolutionize the way we deliver and understand the Earth we live in. And then we want to take advantage to this revolution. Ocean robotic is coming as well. There's 2 types of robots under the water. You can power them through a cable from the deck of the ship, and then you can turn on your diesel engine and then provide the fiber optic cables. You can run your, we call it ROVs, remote operated vehicles. You can take pictures and take videos and collect environmental data sets. Or you can make the robots autonomous, saying, I don't have a tether, let's swim outside for 10, 20 miles. And that's the vehicle used to search the black box for the MH370. There's a problem, because after how many hours the battery will die, and then you have to take the big machine back to the deck, and you have to plug in the diesel generator as well. So regardless which type of robot, is a tethered vehicle, autonomous vehicle, charging batteries at sea is a very expensive operation. It's just not scalable. And scientists getting smarter, engineers, smart engineers, and start to develop a more and more autonomous system. So we can get rid of the ship, so we can let the robots to work on themselves. This is one of the simplest type of robots in the last 20 years in the community have developed. It's a vertical takeoff vehicle. Think about a hot air balloon. And here you can see you can have a pump to changing the volume of the oil bladder. And then by changing the volume, you can change the buoyancy of the device, and they can move up and down, just like the hot air balloons. And you can drop from the ship, you can drop from the plane, and they're fully autonomous. You can tell the robot how deep it go, and then do A, B, C, and come back and talk to satellites, and then go back to do the work again. It's a remarkable machine, and then the community have deployed thousands of these. It's one use case study, try to monitor ocean temperature using these robots, and then UN required take about 4,000 data points for the global ocean to monitor how quickly and how deep the temperature is warming in response to climate change. But there's a problem. We reached the goal of 4,000. There's a lot of green dots here. Oh, the green dots showing that the robot's still reporting data every time it comes to the surface. And at the same time, you see a lot of red dots at the same time. And what are those red dots? And they are dead robots, right? So after a certain amount of time, the battery dies, the robot dies with it, because it costs more money to go out to retrieve them, to charge them on the ship. So typically of these robots cost about maybe $50,000 plus minus 50%. And to recover, to replace them, recharge them on the debit ship costs even more. So typically it's considered as a disposable device. So not only financially it's costly, it's not sustainable, environmentally it's impossible to imagine as we scale up into ocean exploration, into many other use cases. This was a single use case. I put a simple mathematics there. Typical one of the robots take about 6,000 kilojoules of energy. That's a measure of energy, kilojoules. And then just give you a reference, a typical car battery about 3,000 kilojoules. Can charge your car and then run for a while. And AAA battery is about 3 kilojoules. So basically each one of the robots carry 2 car batteries. Or you can imagine 1,000 of these dead every year on the order. So you can think about 2,000 of these car batteries basically we throw in the ocean. Or you can say we have recycled AAA batteries, or it'd be 2 million of these batteries being thrown away every year, just to monitor one particular study. Clearly it's not sustainable. There's more sophisticated robots are being built. This is what we call underwater gliders, and they have a wing on each side. As the robot's going up and down, they can translate the vertical motion into horizontal propulsion. They can pitch roll and let the glider to go certain directions, just like you do the air glider. In the same way, you glide in the ocean, you can carry sensors to detect marine mammals. You can hear submarines. You can measure environmental parameters, water qualities. And then very quickly, you will realize this smart machine is also powered by batteries. And then you can see changing battery is also a very challenging operation. You not only need big ships to find the robots in the middle of the ocean, you need to lower your small boats, and then people go there and then recharge battery, swap a battery and let them go for another mission. Even though the machine costs $250,000 each, I visited one of the sponsors. So the robots spend more time in the warehouse than in the boats. This is the US Navy, the biggest customer of this particular machine. And they don't have enough ships to recharge the battery, even for biggest customer of the Navy. So, so about 10 years ago, the community started asking, how do you power these drones? We see this drone revolution is coming. We see gonna be thousands, if not millions of robots in the future, in the next few decades. How do you power them? You know, clearly throwaway battery is not a sustainable solution. People try to develop fiber optic cables, and then so we can have a plug extension cord on the sea, right? So people have done it. National Science Foundation spent the biggest amount of funding in oceanography, lay about 200 miles of cable off the coast of Oregon and Washington, and try to extend the power plug in your room into the seafloor. So you can imagine laying fiber optic cables in the sea, need the special ships. They sell by inches, extremely expensive. It's very powerful to bring the power plug into the sea in the middle of the ocean, but it's one of the decades opportunity. You can do a demonstration. You can charge your drones. You can power your sensors. You can monitor earthquake in real time and try to have early warning system for the tsunamis if there's an earthquake. And it's a very good case study if you can do this in a localized area. It's not a global solution. People have using the well-known source of renewable energy from solar energy, from wind energy. There's startup companies being established in the Silicon Valley in the last decade. The well-known liquid robotic using solar panels on the top, and the wave energy propels. You have almost like a wind shutter. You have, when the wave coming up and down, you start to generate the force, propel the vehicles to move horizontally. It's extremely useful surface drones to collect air-sea information at the ocean surface. That's being acquired by Boeing a few years ago. Sail drones is using wind energy to have these surface drones and then going much faster and then propelled by the wind. You can put the solar panels on the side and power your sensors. A successful company, and then just closed a Series B round last year of $60 million. So it's emerging, have this race to have drones at the surface powered by both the solar, winds, and the wave energy. And as we go dive deeper, and then it's really none of these form of energy is available. So as the deeper you go, the darker it become, and there's just not many sources of renewable source of energy available. So that's where we come in. We started a little bit over 10 years ago getting into underwater robotic and renewable energy, looking into a different form of energy, try to find a source to power them. So with working at JPL, the advantage have 3,000 engineers. You can pick up the phone and get the smartest rocket scientists and rocket engineers, say who can do this, right? Put a team together. So we find an innovative solution to harvest energy from the thermal temperature difference in the ocean. As you know, the ocean is warm at the surface. As you dive into the deep ocean, a few hundred meters, and then you'll become 5 degrees C or even less. So you have this 10 degrees C or 18 degrees Fahrenheit majority of part of the ocean, you have this energy. So the way we generate energy is like a steam engine. You use some kind of working materials. Steam engine use water to boil 100 degrees C temperature difference. You can boil into vapor spin the turbine, generate electricity. Similarly, our innovation here is how to turn a much smaller temperature difference into electricity. In this case, about 10 degrees C or 18 degrees Fahrenheit. For small energy production, we can use solid to liquid transition. We find a material, they are in a solid material like a wax material in the deep ocean. When they come to the surface, they can melt into a liquid, give you about 10-15% expansion. That's turn the thermal energy into a mechanical expansion. They can turn the turbine, generate electricity. For bigger energy production, we'll use liquid to gas, and then we can circulate our liquid materials and then vaporize them, just like a steam engine, except we can vaporize them in a 10 degrees C environments. So the schematic on the right-hand side just show you how this thermal energy being translated into a mechanical expansion, and that's expansion will generate a hydraulic pressure and then turn the turbine, generate electricity. You can save into the storage, and then you can use for future use. So we developed the technology at the JPL. We left JPL to commercialize them and try to take this innovative technology to a commercial application. So we can power a number of different vehicles and then solve the energy problem, as Jerry pointed out early on. There's a lot of ocean exploration limited by power. So power is the topmost challenging problems, prevent us to scale the global exploration. What I mentioned earlier, the vertical diving machines called the floats. Basically, we can attach to one of our systems on the right-hand side to provide 100% power for their operation. So typically, you can imagine is a machine costs $50,000. You can make about 300 dives using the batteries I described earlier. Because we generate energy in the water, so we can provide energy directly in the local site. You can imagine we even double the cost. We can provide essentially unlimited, or at least order magnitude more capability. So that's where we start our commercial sales this year. It took us quite a number of years to take the research prototype to a commercial product. Jerry asked me, what are the challenges? And then I said, the challenge is to take the research to a commercial, is to produce the first product from 0 to 1, and then taking to the customers, and then have a willing paying customers to help what they are doing or they cannot accomplish something in the past. So that's something already commercially in sale this year. And our goal is to replace this a network of floats. As I mentioned, there are 4,000 of these in the water performing a particular task. And I did a little snapshot yesterday. Is is slightly over less than 4,000 of these, 3,600 of them still reporting data on a routine basis. And that's the information we need to provide to the hurricane forecasting models to improve the understanding of the ocean so we can improve our forecast of the intensification of the hurricanes. Forget about the European models and the US models, so I did put a line there. And then the European model in red and the US model in blue. Then for some reason, either they have better computer or some other thing they did right. They are doing better forecasts of the hurricanes.
We got Sharpies.
That's another story. So this is our goal number one, is to at least we try to eliminate the battery disposal at sea. At the same time, we can help scientists to collect data at order of magnitude less cost, so we can improve the information content we are providing. Another new initiative internationally try to call out 1,000 of these devices to carry chemical, biological sensors to measure the ocean health, to try to help us to monitor how the ocean is changing in response to the climate change. What I've shown here in the graph is a data set from Hawaii station, show you how the temperature and atmospheric CO2 going up in that particular site represent the global climate change. And at the same time, as you increase the CO2 in the atmosphere, is more absorbed in the ocean, you start to see a systematic decrease of the pH in the seawater. So that have a fundamental impact to the ecosystem, the species in the water. So that's need to be monitored on the global scale rather than a single station. So we're calling 1,000 of these robots need to carry biological, chemical sensors, particularly measure the pH, dissolved oxygen, or nitrate, and many other sensors, chlorophyll, productivity measurements. So that itself also call in increased power supply, and then we are sustaining a program which is are not doing, not possible before at a certain cost. When the battery dies, $100,000 machine will die with it, right? So now we dramatically reduced cost to collect the data from the ocean. The underwater glider I mentioned earlier, still powered by batteries today. And there was an effort a couple years ago try to cross Atlantic at one point. We have a challenge from Eric Wendy Schmidt Foundation to be the first glider to cross the Pacific. So that's the goal we are aiming towards, to launch from LA, eventually, or ended up in Tokyo and Hong Kong. And then we did want to go around Hawaii for a circle in case something goes wrong. That could be an easy recovery and a deployment place. So typically, a battery costs about $20,000. They can last for a month or two, depends on how many sensors you carry on board. We envisioning our energy harvesting system, you will break even after you replace 2 or 3 times of the battery. We anticipate to release this in the first quarter next year, and to help not only researchers and then different customers to access the ocean in the long term. Looking a little bit down the road, we are in the R&D phase to develop next generation systems, power systems. In this case, we anticipate to have a permanent energy power station. We are generating energy using a slightly different liquid to gas phase transition, so we can cycle our working fluid in the water column, so we can have a continuous power production, hundreds of watts continuous power, and then we can store them into a storage. We can power a different size of the propeller vehicles. The smaller one take about 1 kilowatt hours per charge. The bigger one may take 10, lower tens and kilowatt hours. And we anticipate to install a network of these charging stations and on the order of $1 million each. And we start to sell electricity for those people cannot afford the charging station. So we can sell on the order of $1,000 per kilowatt hours, and then to provide unlimited electricity for these underwater operations. So you imagine you can optimize the network of the of the charging stations, just like you see more gas stations in the neighborhood we are. You're driving out of LA, the next gas station will be 50 miles, right? So it's proportional to the vehicles that you're supporting to. Last year alone, there's over $2 billion of propeller AUVs being sold. So there's thousands of these vehicles in the community need to be powered. So that's the goal we tried to envision. A few years ago, we did a little study at Caltech, tried to develop a methodology to really look at the ocean from satellite in space all the way to the seafloor, to truly understand the ocean in a transparent way, and then combining autonomy with ocean sciences, and then to make breakthrough in a number of areas, and to really taking the information we are collecting in the ocean to help us to make better decisions. So in other words, you can complete the loop from sensing, having a sensor in the robots, to collect the data, to ingest into your knowledge models, and then to produce information and to help you to make better decisions. And that decision will help you to accomplish goals and objectives, and then either to collect information or monitor the health of the ocean farms, and try to answer the question how many sense drones you need to deploy in the next cycle. So by going through these loops, you improve your information content, you can make better decisions. So the first round, you can say, I need 5 robots to collect ABC data to help me to make these decisions. And then tomorrow, you will say, I need to improve another 20% of this forecast, and then to better understand the water quality to inform my farm. And then you need maybe 5 more robots at a particular location. So by iterating this, and then you can improve your understanding, and then make the ocean is a predictable ocean. Similar to the weather forecasting, when we ever go out, you open your phone, you want to check the weather prediction, right? So before you travel, what kind of luggage you're going to bring, and then how many clothes you're going to bring. So there are a couple of future science directions we want to do. We believe we provide the power to the drones. We can implement a number of different drones underwater, so we can start to pinpoint exactly where you are underwater. So it's like underwater GPS. We can follow the Uber drivers around everywhere. And today we cannot follow anything go below the surface. You can track them on the surface with satellites. Once you're below the surface, it depends on your best guess, right? So I think with our persistent power system, so we can provide the information using acoustic, for example, is to pinpoint and triangulate not only the drones we are sending to, but also we can listen. And there's a lot of sound in the ocean. Ranging from the natural sound from the marine animals and to man-made sound, a noise, if you want to call, from container ships, or you want to hear your enemy submarines, or you want to protect the certain species, and you want to minimize the noise, and then you want to minimize the collision, for example. So you want to protect those marine species as well. So better understand sound in the ocean and then try to position them, try to inform us to protect the ocean we live in. Another potential example we can do is to provide a network of powered drones and try to pick particular species you can monitor. This is a use case a colleague a number of colleagues have been conducting research, like including NOAA, and then to understand the population of right whales, and then both in the North Atlantic and North Pacific. It's amazing, North Pacific, and then according to the best knowledge from NOAA, and there are probably less than 40 left. So it's challenging to maintain and grow that population. I think North Atlantic still have a few hundred of them left, and then if we do better monitoring, there's good hope we can minimize the collision, the deaths, and then we can make the population go up to save, prevent in extinct from our ocean. So our power system certainly provide the backbone for the drones and then carry the hydrophones, so you can detect them, you can tag those whales, and try to understand their behavior, their migration, and their habitat, and their population as well. So go back to coming back to home here. Is amazing to see these amazing facilities, and then to you bring these animals for us to see, you'll hear, you'll touch them, you interact with them, and looking into the coming decades, we are in the critical moment to bring a number of different technologies to take advantage of the robotic revolution, and then to bring you to the ocean. Those information you can see become a truly transparent and a predicted ocean, so we can take you into the environment that you otherwise is difficult to access. In terms of the journey from a research scientist to entrepreneur, have a startup companies, is all saying it take a village to raise a child, right? So this is a Seatrec and the passion about to grow in the coming decades, and then I thank to GFPL and Caltech allow us to license the technology to commercialize for applications, as I mentioned, from research to a number of different other applications like farming, underwater communication, defense and security, oil, gas industry, all the way to ocean transportation and navigation. A number of institutions help us along the way. I want to acknowledge early on, Teal Foundations. I have a breakout lab in San Francisco. They become the first institution supporting the company, and then from 0 to 1 technology. Later on, Eric with the Schmidt Foundation, through their marine technology partners, also supporting our glider project. We are fortunate to receive the small business funding from the government, all of you through the tax dollars supporting us. So in other words, you are all our supporters. So 3% of the president's discretionary funding go to the small business innovative research program, SBIR. So that's support company with 500 people or less considered a small business. So we are fortunate to have SBIR funding to support on R&D going through Department of Defense, through the U.S. Navy Office of Naval Research, as well as National Oceanographic Atmospheric Administration. A number of worth mentioning as well. My 2 boys has been really supportive to be curious to become an oceanographer, to discover new things. My wife certainly has been really supportive. Without the family support and support your salary, give you medical insurance to start a company is a key. First few years has been really lucky to have a number of friends. I think the textbook company guidance saying start up a company, you raise money from your friend and family first. So that's a number of people maybe online and watching. Thank you for the support. Starting this year, we are getting support from investors from different local groups. Pasadena Angels has been leading this year's fundraising for us. There's 22 members out of the Pasadena Angels supporting us this year. Takeoff Angels as well, LA and Orange County chapters. And recently we become a portfolio company of Lacey, LA Clean Tech Incubator. And we also received their funding from their impact funds this year. The final person I want to thank is my mentor at Lacey, Bob Musselman. Being a CEO of the founder is challenging from day to day, weekly basis. I appreciate the mentor at Lacey every week being my therapist and listen to my up and downs and provide guidance and otherwise. So I stop here and take your questions.
This is a great story. So, you mentioned the difference in resolution of our mapping of the moon, and Mars, and the ocean. And you did mention that, but I want you to reinforce, one of the big differences, space and the atmosphere, they're transparent to light. The
Correct.
ocean is opaque to light. So we have to have, that's why we need to use sound.
That's correct.
And I think, there's a rumor in Washington these days that later, early next month, that there will be an announcement by the president. He's in a little trouble right now. But that he's going to announce a $2 billion initiative to map the U.S. exclusive economic zone to the highest resolution possible,
Right.
using multi-beam.
Mm-hmm.
And if that happens, that would be really fabulous, because more of the United States is underwater than is exposed.
Mm-hmm.
It's rich in resources. And have you heard this rumor that it's going to be CEQ and the Office of Science, Technology Policy will make this announcement?
That's a great news. I think California is always leading the nation, right? So California, a few years ago, invested about more than $200 million to map our own coast, and they take a few of these vessels, the multi-beam. By multi-beam is looking aside of the ships, and then they can create a wide swath coverage. So it's rather efficient, it's very power hungry, and then it can sweeping through the coast. Take about a couple of years to map the entire California coast. It's a pretty high resolution. I think it's great to have the nation to have that kind of mapping capability. And there's a number of different other technology. Can have a single beam that's called echo sounder. In other words, you can send a ping to the seafloor by listening to the return, measure the time. You can measure the seafloor that way by knowing the sea level. So that way you can measure on every robot in the future. I will advocate, if energy is not a limitation, you should carry this sensor to provide the data to map the seafloor. So we definitely want to do better than 5% as we move along the next decades.
Yes. And it's interesting that one of the things that we learn is the variability and the complexity of the ocean by having more data. And as we're changing the temperature and the chemistry, we're putting a lot of sea life at risk.
Correct.
And yet, as one of your slides showed, there probably are areas that could be refugia for species because the pH isn't changing as much, the temperature's not changing as much. We need to find those areas and,
Exactly.
and to protect them.
Right. We need to monitor on the global scale as well. There's a few stations. We have been monitoring them regularly, and there's a few time series and on the fixed site. There's certain anchored moorings and the stations we're doing those measurements. But as you know, the sea level changing differently in one state, and they have different sea level rise in another state. Same thing for the pH. So you need to monitor on the global scale on every part of the globe.
All right, who has a question? Let me bring you a microphone so the people who are watching online can hear.
Thank you. Thanks for a great talk. What do you find is sort of the most politically motivating argument that you can use, when people are getting into this? I see that they're sort of building, what's the word I'm looking for here? Building momentum around this, but what is working as a driver here in the U.S. and sort of globally?
It certainly is an international effort. As you know, the UN recognized, and then they declared the Decade of the Ocean is this awareness for not only the developed country or developing country to work together because everybody access their own ocean. They take the whole international community to improve what our understanding, our knowledge. And then there's a number of arguments we can make. Is the ocean provide a number of different key information for the life and death. Hurricane prediction is one of them. In the last 20, 30 years, no matter how fast computer we are building, we have almost no progress forecast intensity. We do better on track prediction. We can see the satellite. We can do the track pretty much better than 20 years ago. But we have no idea why the hurricane intensified within 48 hours from category 3 to category 4 or 5. So every category, as you know, imply the danger of the population, how many people have to evacuate it. That's just one example. pH, Jerry mentioned, is another good example. A number of these ocean water qualities, and then as we put in more offshore farming into the ocean, We need to know better ocean conditions, the health of the water, and to better inform on those farming industries, and then to provide enough protein to the growing population. So there's a number of different, not only curiosity-driven science, but also societal, practical, relevant questions we can address.
And this country was founded as a maritime nation. No other, France claims they have a larger EEZ because of some of their territories. But if you look at, we're bounded by the Atlantic, the Gulf of Mexico, the Pacific, and the Arctic, and yet we've isolated ourselves too much, and we're too preoccupied with building walls.
You're going to let us know when you go public, right?
Everybody funded us through the small business grant, so basically everybody is stakeholder in this game.
Okay. Now, since your power is generated by temperature differentials, do your units are attached to current technology drones, right?
That's a portable system I mentioned earlier. Our power station will be a standalone system. It's much bigger volume and weight, and then will be standalone, not attached to the drones. So the drone will come back to get charged once they need power. This is similar to the how many miles your EV or your car can drive, and you have to go to the gas station or charging station.
But if you need a temperature change, don't you have to move up and down in the ocean?
Yeah,
to create that differential.
For the portable, you move up and down. For the power station, our working fluid is cycled through the water column, through the cold and warm. Okay. So we continue to vaporize our liquid as they cycle through, so we can have a continuous power generation. That's the only way we can reach the kilowatt range, rather than a few watts and tens of watts.
So in some ways, for your technology, global warming is good. It heats the it heats the surface of the ocean more.
The energy we convert is negligible.
No, I understand. It reduces it increases the stability of the water column.
Only the most accurate sensor can detect the difference. So you touch the water, you cannot feel the difference.
Thank you very much for all your information. It was quite interesting and informing. The drones that lose life, so to speak, that are laying in the bottom of the ocean, I was wondering about the effect they have ultimately on the water in the ocean and the marine life, and does the marine life get affected by the drones? And if so, what effect is having on them, and do sharks maybe take them for food? Now, I think maybe I've asked you a three-phase question. It was meant to be one, but okay. I have parts to it, so thank you.
So let me try to address one at a time. I think most of these drones are too big for the sharks. The only case, the most amusing story I heard is one of the gliders get lost for a couple weeks because they lose communication. Usually they come to the surface and then report to health and then take command to do the next mission. This is the operation. Suddenly gets stalled. The glider never call home for many weeks. And then eventually a few weeks later, you'll hear the beep and then it's calling home. And then eventually they get recovered, and then they discovered there's this mark. I believe the first giant squid try to hug for a couple of weeks and then eventually abandon the gliders. It's just not fun. It may not be tasty at all. So that's kind of one of your questions. The other question about the battery life, certainly as we grow the technology and then beginning of the robotic revolution, we start to realize that more and more batteries put in the ocean potentially can be harmful. There's no regulation today you have to take the battery back after the end of the life. But hopefully that will come as we mature the industry, mature the technology, and reduce the cost. And there's still a big cost to recover those batteries. Once they get disposed, we only know the last reporting position at the surface. We don't know exactly where they end up. So even though we know where the surface could be many, many miles in a different place. Certainly, I can create a video to show you 2-car batteries and what they look like when they explode, right? So there's a potential danger if you're really nearby. It's really the question is how scalable and sustainable this particular approach as we scale up. We have a major conference last week in Hawaii every 10 years to plan the next decades. And then we're calling for 10 times, 100 times, or even 1,000 times more drones in the ocean to help us to make better decisions. So as we getting into the next decades, clearly this is an issue the community have to address. And then eventually we have to minimize or reduce, eliminate harmful chemistry-based batteries. I keep asking that question to many faculties and professors and doing, especially in the chemical oceanography and chemistry. Certainly that's need to be addressed. It's just the magnitudes, right? So how much we're going to put in the ocean. 20 years ago, we think, and plastic in the ocean is not a big problem. The ocean is big oceans. They can take infinite amount of trash, right? So now you see one straw at a time and it make a difference. So I think the sooner we understand the impact, that's a great question to understand it and then make action to prevent it happening.
Next question. Raise your hand, I'll bring you a microphone. Who has one? Somebody must have one.
Was any consideration given to using a radioisotope thermal generator for power?
For certain customers, they probably do it already, so that's for mass customer, broader customers. Certainly that's, if you, it's still a thermal energy generation. If you can generate 10,000 degree temperature in the little, lunch box, and certainly that's the best source of energy. Certainly manned vehicles are willing to take that risk. Many of these unmanned vehicles, and then unless it's special circumstances, I would imagine the management of the waste and then the consequence will be severe enough to prevent a broader uses of that kind of energy. Does that make sense?
So when you have unlimited energy, it's amazing what you can do. And there are different kinds of energy that serve different purposes, and you have found a niche.
Right.
Describe that a little bit, because as we talked over dinner, there isn't any single solution to this energy problem.
There are a revolution, as I mentioned, on the surface robotic vehicles, unmanned ships, unmanned surfboard, unmanned wind-driven drones. So there's a number of companies and started in the last decade to take advantage of these different source of renewables. Solar at the surface, solar energy, wind energy, wave energy. They all enable certain type of surface platforms, and they can easily to navigate on the surface. They're collecting very important weather information in the air and the near surface information in the ocean. So we are complementary to those surface drones, and then provide the submersible and then deep ocean drones, and then provide a source of energy locally underwater, and also producing platforms and energy harvesting stations underwater is much cheaper than the surface expression. If anybody build any structure near the surface, it's very costly, it's hard to maintain. And then you go 50 meters down, it's really nice and calm.
Since you seem to be addressing lots of different parts of the puzzle here, do you see any good upcoming innovations in, say, the total communication path? So let's say you're collecting data down deep, and you have some total energy cost to get your bits back to a computer on land. Is there anything good coming up in that realm?
Can you elaborate your questions more specific? Yeah, there are certain advantage to go deeper. And for example, one example I can give you, the vertical drones, and we designed 2,000 meters, and then we think global warming and warming ocean, maybe a few hundred meters, 200 meters is pretty deep, right? So after 20 years of research, we find out there's still ocean heat unaccounted for. So there was a period of time we don't really understand where this heat's going. We know how much heat we are getting, and then we cannot close the budget, right? So it turned out a lot of the leakage of the heat go deeper than 2,000 meters. Now we're designing robots go down to 4,000 meters or even 6,000 meters, try to map the entire ocean. I'm not exactly sure.
But I think you had more in mind when you gather all this data from the ocean. How do you get it back to people? So say when you come to the surface, you can transmit that to satellites, and satellites can get it to your laptop. Is that?
So the last time I used Iridium, right, it was really expensive, and you could send 1,600 bytes or something.
Yeah, certainly software, AI, is machine learning, all these new tools become available or make those dramatically reduce that data being returned to your laptop or your smartphones. There will be certainly a software revolution as we collect more data. And as we gather more sound, we gather more images and videos, and there's absolutely no way we can send back everything we're measuring. So onboard processing, more power, faster computer, powerful software to compress the data, to even process the data, to send the valuable information rather than raw data. So that's tremendously helpful. Satellite communication is still pretty expensive. We have to pay every bit we're sending through satellites, like your cell phone. You still have a limitation how much data you can send back. Underwater communication, acoustic, we can use acoustic to transmit data, but it requires a very dense network, so it's still not globally available today.
You really still have to come to the surface.
Most of the time, you come to the surface through satellite.
And then disperse.
Correct.
Right.
Yeah. There is a regional acoustic network you can communicate and then kind of relay through acoustic data transmission to a certain place, and then it's still you either go to shore or you come to satellites, so either one of the route.
And you still need the people on shore to translate those data
That's
into
correct.
information
That's
to make better
Yeah.
decisions.
Yeah, you need more drones, you need more software engineers to compress those data and process them.
In regards to hurricanes and predicting them, how much progress has been made towards that? And once you receive some information, who's the backup people to move forward so it'll be sooner than later that you'll find the information that you need to find?
As I mentioned, there's a tremendous progress to monitor the path of the trajectory of the hurricanes, the track of the hurricanes, not only through satellite measurement, but also U.S. have a fleet of aircraft, if you heard on the radios and TVs, and then the hurricane hunters. So they basically fly into the eye of the hurricanes. And remember, you heard a story, they fly to the place, they cannot find the eye because the hurricane moved 10, 20 miles away already. So those very valuable information collect the information inside the hurricanes. What is missing, I believe, is this underwater. We know the temperature is warm. That's why hurricane happening in these warm, nice places, because that provides the fuel of the hurricanes. But what we don't know is how deep those warm water will penetrate. So that's the key information to give you the intensification of the hurricane. That's the poorly known quantity. And then if you talk to the National Hurricane Center, in the last 2 or 3 decades, there's very little progress improving that prediction of the intensification. And that's, I believe, the ocean, deep ocean information hold the key to many of those cases.
And the administrator of NOAA once said, and another big challenge is figuring it out how to convey that information to the public so they will pay attention to it. And that's social science.
That's beyond my expertise.
Yeah. All right, we'll take one more. Anybody have one? Val?
Hi. I want to build on Frances's previous question, her first one, about the dead batteries. I'm not concerned about the dead batteries as I am as the entire mechanism, the float itself. If you've got 4,000 of these, and if many of them die, they go down to the bottom, as I understand what you're saying, and create ocean litter. Mm-hmm. And how is that going to be dealt with?
Well, certainly, number one, we need to create awareness that's happening. Number one, as we have this revolution in the next decade, we're going to have order of magnitude or two order of magnitude more drones, right? So the disposal is a major challenge. Once you create awareness, you understand what the impact the local ecosystem and then impact the ocean. And then the third question is, how do you either reduce the use of this chemistry-based batteries, or you find a way to recover once they die? Maybe rather than send them to the bottom, to let them float to the surface, and then the next ship coming by, maybe a fisherman can pick it up and then call 1-800 number, give them $1,000.
Go back to that map that showed all of the floats.
Just to give you an example, there's even we put in about 1,000 of these. They say for one particular use case, it's one particular project require 4,000 of these drones working, and they put thousands of them die per year. So accumulative is tens of thousands already.
But the other I
They owe
think
them.
the other point is that if the size of the dots were scaled to the size of the drone, you wouldn't be able to see them probably
Of course.
on this map. So it's
Yeah.
not anywhere near as bad as it appears.
Yeah.
That doesn't
Those are-
mean that we shouldn't be worried about it.
Yeah. But as we go, a million drones, now we have a
Yes,
problem.
now- right.
And this is a particular one use case, and then that's the last position. We don't really know exactly where they end up because ocean or ship them away somehow. It's like you have missing airplane, even though you know the location, your black box could be anywhere within tens of miles.
But I think Yi has. Hilden, did you have a question?
Yeah, would they be animal habitat? I mean, are they that big where they don't?
Not the chemistry, not eventually the chemistry, or you can go to YouTube and find those videos and then what the consequence when they explode.
But this is an important contribution that you're making to ocean exploration, and it is a story we want to tell here.
That's the challenge, is to mature this technology and then bring the awareness, and then to use the clean energy. We have the technology today. We can prevent this happening
That's right.
in the next decades.
So you can bring those right back home. Those.
Or we stop using chemistry batteries and a renewable source available. So it's power. We measure the sea and then power by the sea. That sounds better.
You went one more. Go ahead. Nice and loud.
How deep can those renewable energy, like submersibles, go down? How much do they impact on our research?
Some of the submersible go as the deepest place, 10 kilometers, and then typically most of these ocean depths on average about 4,000 meter deep. So that's kind of on average. Certainly you have those trenches going twice as deep or even more. And then some of the exploration, there's a few times people can go to the deepest places and then find plastic story, even in the deepest places. So typically for most of the applications, maybe 1,000 meters is enough, particularly monitor the health and the productivity, the farming. There's most of the activities happening in the upper 1,000 meters, even a few hundred meters, where you have light, you have a marine life, abundant life, and then typically those are the most active places in the first 1,000 meters.
Yeah, we want to thank you for a terrific lecture and
Thank
for
you very
everything
much.
you're doing.
Thank you for your time.
And our next lecture is October 8th. Lee McIntyre will be here to discuss his new book, The Scientific Attitude. Very important. You don't have to be a scientist to have a scientific attitude, and not all scientists have a scientific attitude. So I would encourage you to come, because this is trying to look into why in this society is science not enough. Why do we have these debates about whether climate change occurs or not? Why do we have the debates on the science of whether vaccinations prevent disease and so on? He's written a fascinating book, and I would encourage you to come. He may make you mad, but that's okay. We'll see you then.